You hear about digital twins everywhere, right? They're hyped up as this massive revolution for industry, promising to change how we run our plants. But there's let's call it a dirty little secret the sales pitches don't always mention.
Why is it that these super expensive, incredibly powerful tools, the ones that look so amazing in a demo, so often just fizzle out? They get built, they get deployed, and then they become just another dashboard that nobody on the floor actually uses. What is going on there?
Well, let's get right into it. The answer, when you really boil it down, is shockingly simple. It's the massive gap between the clean, predictable world of a computer model and the chaotic, messy, unpredictable reality of a real-life industrial plant. And it's in that gap where almost every digital twin starts to stumble and fail. So that brings us to our first huge problem area, this fundamental clash between the pristine assumptions baked into a simulation and what's actually happening on the plant floor minute by minute.
See, most of these digital twin models, they're born from an idealized version of the plant. They're built for this perfect world scenario, assuming everything is running smoothly, under stable, predictable conditions, the kind of world you only find on an engineering blueprint.
But come on, anyone who has actually set foot in a refinery knows that's not how the real world works, not even close. Real plants are alive. They're constantly dealing with swings in feed quality, equipment getting fouled up, instruments drifting. It's just a constant stream of imperfections. That's just a normal Tuesday. And this is where that conflict just becomes crystal clear. Look at this. The model assumes stable, predictable behavior. The plant is dealing with constant disturbances and fouling. The model assumes a perfectly known, consistent feed. The plant is getting these messy, blended, variable streams. The model assumes perfect automated control. The reality is, operators are constantly jumping in and making adjustments. It's no wonder a tool built for one world is basically useless in the other.
So, okay, the model itself is already standing on some pretty shaky ground, but it gets so much worse when we look at the data that's actually feeding this thing. This is what we call the imperfect data problem, and honestly, it's a massive hurdle.
So let's start at the beginning, the input. In a lot of these complex refinery units, you don't actually know the full feed composition in real time. It's impossible. So engineers have to rely on estimates, using these simplified stand-ins called pseudo-components and making educated guesses about the blended streams. The feed can change with every new crude slate or tiny bit of contamination. Basically, the plant often isn't even processing what the model thinks it is.
And that right there is the crucial point. It's that old saying, garbage in, garbage out. But it's even more dangerous because it's not always obvious garbage. If your starting point, the very foundation of your model, is just an estimate, then every single prediction that model spits out is automatically built on a foundation of uncertainty.
And it's not just the inputs. Think about the outputs, the stuff that really matters for performance, like product quality, viscosity, composition. These things are almost never measured online in real time. You're waiting on lab samples. That means your data is hours old. So the digital twin is essentially flying blind, trying to predict things that the plant itself can't even see right now.
And this is where all that hype about AI and machine learning just slams into a brick wall. AI models, they need beautiful, complete, consistent, perfectly labeled data to work their magic. But real plant data? It's the exact opposite. It's incomplete, it's noisy, it's inconsistent, and it's often poorly labeled. If you train a model on that messy data, you might get something that looks right on paper, but it's going to break the second conditions change in the real world.
Okay, so we've painted a pretty bleak picture, right? We've got a disconnect from reality and we're feeding it imperfect data. But the solution isn't to just throw up our hands and abandon digital twins. The solution is to build them smarter, and we do that using something called a hybrid approach.
So what on earth is a hybrid digital twin? Think of it this way. Instead of trying to build a model from scratch using only that messy plant data, you start with a strong foundation. You start with first principles. That's the basic laws of physics and chemistry that we know govern the process. Then, and only then, you use machine learning and real plant data to correct for all that real-world messiness. You're using AI to bridge the gap, not to build the entire bridge.
So here's how those ingredients come together. You start with that fundamental process knowledge, the physics. Then you overlay the real-time data from the plant. You bring in those crucial but delayed lab samples, maybe using soft sensors to estimate what's happening in between. And then you layer machine learning on top as the final smart correction factor, constantly nudging the model to match what's really going on.
But listen, the tech is only one piece of the puzzle.
you have to follow some rules. First, build the twin for a clear, focused purpose. Don't try to boil the ocean. Second, you have to constantly check it against real data, or it's going to drift away from reality. Third, and this is huge, you have to design it for the operators, to answer their questions, not an engineer's. And finally, the model has to be honest. It needs to show you where it's confident and where it's just guessing.
When you put all this together, you start to look at success in a totally new way. It's not about who has the most complex model, it's about who has the most useful tool.
At the end of the day, a digital twin doesn't fail because of some complex algorithm. It fails for really simple human reasons. It fails when it stops helping people make better decisions. It fails when the folks on the plant floor stop trusting what it says. And it fails when it just stops looking like the plant they work with every day.
And at that moment, it stops being a living, breathing operational tool and it just becomes, well, a digital artifact, a relic. It's something you can look at from a project that happened a year ago, but it's not something you use. And that is the real failure we have to avoid.
So the goal here isn't to build the biggest, most complicated model imaginable. The goal is to build the most resilient one. You want the one that actually becomes more valuable when things get messy, when the plant drifts away from that perfect ideal, which, let's be honest, is pretty much all the time.
So I'll just leave you with this question to chew on. In a world full of messy data and plants that never behave perfectly, how do we shift our thinking? How do we start designing our advanced tools not for the perfect world of a blueprint, but for the imperfect, dynamic, messy reality they're actually supposed to serve?